is in gray is not significant. What is in white and black is significant. And this is trial done by trial based. That is how it was judged. If you look at slide 63, of course, wave propagation is also connected to synchrony. You can't have waves that are developing over the Utah area without having any synchrony between the electrodes, of course. One can't do without the other. And the left two plots show the wave thingy, and the right plot you've already seen is synchrony level. So there is some correspondence. And on the left side, I've marked for the under-rewarded case a region labeled A1 and a block labeled A2 for the unrewarded. But for the rewarded case, I could only label a block A1. I couldn't label a block A2. And that's of course a bit weird. So why is the reason for that? And this is shown in slide 64. It seems if you plot the speed that the wave propagates at a higher speed in block A2 region for the rewarded case than unrewarded. And there was a sampling problem here. So it moves so fast that you have a sampling problem. This could not be foreseen when the data was collected. So the sampling rate was not sufficient. But anyway. Okay, now we get to how you build up your feature space. So you have seen three types of analysis in terms of wavelets, in terms of synchrony, phase synchrony, and in terms of wave propagation. Now you have to define features. And in case of the wavelets, we took 100 features for two electrodes, 18 and 80. So these are 200 features in total, 100 for electrode 18 and 100 for electrode 80. And we look at the extremes of the wavelet scalograms. Remember, I indicated to you these blue little squares. They are the points where you have the biggest difference between rewarded and unrewarded case. So you take those top 100 for each of the two electrodes. Then we move to the synchrony features. Here you take the 150 best separable, and when you calculate the synchrony over 30 millisecond bins, so you compute them across time. You pick them up, what best separating the two cases we're interested in. And then similarly for the wave propagation features, you take angles and velocity magnitudes, and you do this t-statistic, and you keep the 150 best ones. So in total, we have extracted 500 features that we're going to use. And I'm now on slide 66. We then apply a wrapper, and we talked about it in one of our first classes where we talked about machine learning. So this is a selection method that selects individual features to compile a set of them in combination that yield the best classifier performance. Then as a classifier, now on slide 67, you take LDA, a linear one, you'll know this one as well, and so a simple one. And then we have to do it by the book. We have a training set, and we have a validation set. So the training set and validation set should not be overlapping. And then, of course, you will cycle that several times to have every data point become also a validation as well as an element of the training set. So we use 5-fold cross-validation. And then we come to some results, slide 68. Slide 68 shows left and right is monkey 1 and monkey 2. Let's look at monkey 1, the left panel. You see here as a function of training days, the accuracy of the classifier in predicting if the single trial is correspond to rewarded stimulus or non-rewarded stimulus. And you see that the blue lines are actually spatial features. The blue lines are doing a job, they're relatively nice. So sometimes something hovering around 80% prediction accuracy. The red line is actually the wavelet coefficient, so that one is a bit better. So that's a temporal feature. The red line is a bit above the blue line. And then, of course, as you can guess, if you combine everything together, that's the black line, you get the best performance on single trial. So it means that you are using the decoder on today based on what has been trained for the previous day. So you're actually splitting also whatever training and so on you do, you don't do it on the current day. So this is also indicating stability, but also to make the comparison fair. So the black line is toppling like 90%. And then you have the vertical red line where the switch is happening. You see then there is a dip, as you can imagine, because initially rewarded becomes underrewarded and vice versa. So this is what the model also predicts, of course. And then you see the magenta line is actually the classifier that has been trained on the day before the switch, and you continue to use that one. So this is then also doing pretty well. So it's a bit below, but you see that after the switch it is picking up as well. So yeah, you see the difference with monkey 2. Monkey 2 gives something similar than monkey 1. This, of course, shows you what you can do with the different features. The wrapper has picked up the interesting features. I'm now on slide 69. If you want to combine them, then you can ask, when you combine it, then you can ask, like, what is the contribution of these different feature types? Which feature set works better than another feature type? So here you take another approach, so you actually use the features that has been defined by the wrapper, the GMDH wrapper, the wavelet coefficients for the 2 electrodes, synchrony and wave features that have been identified with the wrapper. You use that one, and you train 4 classifiers. So you train a classifier on each case. So you a classifier on the wavelet coefficients with electrode 80, a classifier on the ones from electrode 18, and a classifier on the synchrony features, and a classifier trained on the wavelet features. Okay, and then they combined using the ADA boost algorithm, which is a combination technique. What you get there is a lower accuracy than we had before in what we just showed, but interestingly, we can now judge the contributions. The contribution coming from the wavelets of electrode number 80 was almost 35%. Those from electrode 18 was 59 almost percent. So these are the most successful ones. And then the synchrony 18% and the wave-based 17%. So this shows what is contributing to the success of our classifier. Okay, so this was all for local field potentials. This is just particular. You can use. You can look at other cases, of course. Interestingly, using the same sort of setup, we also looked at what you could do with spikes. I'm now on slide 71. Here you had similar stimuli. So you had these undulations, Gabor gratings. We talked about it before. So it's sinusoidal undulations. And again, there were different orientations, in this case, 8 different orientations. And there was also a noise stimulus, and indicated on the top right. Everything was doing fully and so on. The task was very simple. The task to the monkey was to keep fixating. And then if that was successful, the monkey received reward. Here the decoder is built differently, not predict the juice reward, because the juice reward is now only related to foveation, but here we want to discern the different orientations, the different angles of orientation. And we were, to make it a bit feasible, we have been grouping according to, we didn't look at spatial frequency, we just looked at orientation. If you look at slide 72, you see on the top left this different traces that were spikes that have been detected. everything looks a bit demoted and very blurry. If you would do spike detection, as I said, and you plot the two first principal components,